Imagine walking into a car dealership, right? You're looking around and you have these two options sitting right there on the lot.
Okay, I'm picturing it.
So car A has significantly more horsepower. I mean, it gets way better mileage, and it's priced like 40% cheaper than car B.
Well, the rational choice is pretty obvious there.
Exactly. You'd buy car A in a heartbeat. But then you look at the sales data and you see that 86% of the world is still buying car B.
Which completely defies standard market logic. I mean, when a competitor brings a cheaper, faster product to the market, that is usually the exact moment an industry flips.
Right.
But here, the raw specifications on the data sheet are they're effectively being ignored by the biggest buyers on the planet.
Which is wild. And welcome to today's deep dive, where our mission is to decode this massive mystery in the tech world. We've got this fascinating briefing document in front of us today.
Yeah, it was originally aimed at government IT procurement officers, which makes it super interesting.
Yeah, it's titled AI GPU Podcast Episode 2 NVIDIA Lock-in and Matrices. And we are going to extract the real reason why developers, researchers in these massive enterprises are just utterly addicted to NVIDIA. Even when, like we just said, cheaper alternatives absolutely exist.
And we're also going to demystify the underlying math, right? The linear algebra that secretly dictates this entire global monopoly.
Yes, exactly. Yeah. Because you really can't separate the two.
No, you can't. The business monopoly and the mathematical equations running underneath it are inseparable. You really cannot fully grasp why this market behaves the way it does until you understand how the software actually talks to the math.
Okay, let's unpack this. Here's the core paradox staring us in the face from this 2026 briefing. So AMD currently offers their Instinct MI300X and MI355X chips.
Right, they're flagship stuff.
Yeah. And on paper, these are absolute monsters. I mean, they offer higher theoretical compute power, more memory bandwidth, and a massively expanded memory capacity compared to, NVIDIA's equivalent generation.
Yeah, they really brought the heat on the hardware side.
They did. And they are doing all of this at a 25 to 40% lower cost per unit of inference work.
Which is that kind of discount on superior hardware should be an extinction-level event for a market leader.
You would think.
Right. Any chief financial officer looking at that cost-to-performance ratio would immediately mandate a switch. Like, it wouldn't even be a discussion.
Yet, NVIDIA commands a staggering 86% of data center GPU revenue.
It's crazy.
So, to understand why companies aren't just buying the cheaper, faster AMD silicon, we have to look away from the physical chips entirely. I mean, the moat isn't forged in silicon.
No, it is written in software.
Exactly. Specifically a platform called CUDA, which NVIDIA has been building, refining, and deeply embedding into the tech ecosystem for, roughly 2 decades now?
Yeah, about 20 years. And 2 decades of compounding advantage is the key phrase there. We're looking at a platform with over 4 million registered developers.
4 million, that's huge.
And 40,000 organizations. But it isn't just about the sheer number of users. It's about how deeply that software integrates into the daily operational realities of those organizations,
Yeah, reading through this procurement briefing, it totally reminded me of vendor lock-in with enterprise networking gear.
Oh, like old school telecom stuff.
Yeah, exactly. Like if you have a massive data center running entirely on one specific vendor's switches and routers, your entire IT team's muscle memory is built around that vendor's command line interface.
All their habits.
Yeah, all your internal documentation, your automated monitoring tools, your deployment scripts, they all assume that specific gear. So, when the network goes down at 2 a.m. on a Sunday, your engineers know exactly how to troubleshoot it.
Which means if a rival vendor comes along and offers you hardware that is 30% cheaper and pushes more data, you still don't buy it.
Nope.
Because ripping out that hardware means you aren't just swapping physical boxes. You're committing to a massive, agonizing retraining and retooling project for your entire engineering organization. The friction of the switch costs way more than the discount on the hardware itself.
And CUDA lock-in works exactly the same way, but multiplied across the entire global AI industry.
Yeah.
The briefing refers to this as accumulating in a lot of small technical decisions. It calls it a death by 1,000 APIs.
That's a great way to put it.
So let's look at the actual mechanisms that trap developers. Where does this lock-in physically live in the code?
Well, it starts with highly specialized libraries. So NVIDIA didn't just build a compiler. They built extremely specific software libraries that do all the heavy lifting for developers.
Okay, like what kind of libraries?
You have cuDNN for deep learning primitives, cuBLAS for linear algebra, and TensorRT for inference optimization.
So instead of an AI researcher having to manually write the complex mathematics for how a neural network processes data. They just call a pre-written function from cuDNN.
Exactly. And crucially, those pre-written functions are incredibly fast, because we need to talk about how software actually makes hardware faster. So NVIDIA engineers use techniques like kernel fusion. Normally, if a chip has to do, say, 3 math operations in a row, it calculates the first, saves the result to memory, fetches it back, calculates the second, saves it, and so on.
And I imagine all that fetching and saving takes massive amounts of time.
No, totally. It's super inefficient. So kernel fusion combines all 3 operations into one seamless step on the physical silicon, avoiding the memory fetches entirely.
Oh, wow. That makes perfect sense.
Yeah.
The software knows exactly how the physical pathways on the chip are laid out, so it routes the math in the most efficient physical way possible.
Yes, exactly. And then you scale that up to distributed training. I mean, training a massive frontier AI model requires thousands of GPUs working in tandem.
You have like whole warehouses of them.
Right. And they all have to share their results continuously. So NVIDIA built the NVIDIA Collective Communications Library, or NCCL.
Okay.
And over the last decade, AI engineering teams have built massive amounts of infrastructure around NCCL's specific timing assumptions, its failure handling protocols, and its data routing behaviors.
So if you try to swap in a different brand of GPU, all those thousands of micro assumptions about how long a data transfer should take suddenly just break.
They completely shatter. Yeah.
And then you have the community aspect, which might be the stickiest part of all.
Absolutely.
Because every cutting-edge tutorial online, every answer on Stack Overflow, every piece of pre-trained model code on GitHub, they all just default to CUB.
Yeah, if a developer hits a weird bug on an NVIDIA cluster, someone on the internet has already solved it.
Right. But if they hit that same bug on a competitor's hardware, they're diving into undocumented territory. I mean, they basically become the beta testers for the competitor's software stack.
Exactly.
But let me push back here for a second, because this is where the industry conversation gets really noisy. AMD does have software.
They do, yeah.
They have ROCm, which is their open source alternative. And they have a tool called Hypify, which is literally designed to translate NVIDIA code to run on AMD hardware. So if major frameworks like PyTorch have official support for ROCm in 2026, why can't developers just, hit the translate button?
Well, Hypify is a fantastic tool for high-level code, but the translation falls apart when you hit the basement of the software stack.
The basement?
Yeah, like AI developers constantly write low-level code called kernels that are hand-tuned for NVIDIA's specific chip architecture. They use very NVIDIA-specific tricks like custom intrinsics.
What's an intrinsic?
An intrinsic is basically a way for a programmer to bypass standard high-level code and send an instruction directly to a specific physical wire or circuit on the chip.
Okay, so if I write code that specifically tells a piece of data to travel down a certain physical pathway on an NVIDIA chip, an automatic translator can't just move that to an AMD chip because that physical pathway literally doesn't exist on the AMD silicon.
Exactly. The translator fails, and the developer has to rewrite that hyper-optimized kernel by hand. And we are talking about highly specialized engineers whose time is incredibly expensive.
Yeah, they do not want to spend months rewriting perfectly functioning code.
No, they don't. And this brings up a staggering reality about real-world performance. Because of these deep manual optimizations, the kernel fusions, the custom intrinsics we just talked about, independent analysis in 2026 shows NVIDIA's real-world throughput beats what its raw hardware specs would predict by anywhere from 30 to 99%.
That is wild. I mean, a chip that is technically weaker on a spec sheet is outperforming the competitor in the real world by up to 99%, purely because the software is hyper-tailored to the silicon.
Yeah.
The hardware gap is closed, but the software gap is doing all the heavy lifting.
Which is why the industry is starting to realize that asking developers to translate their code is just a losing battle.
So what's the alternative?
Well, we're seeing a totally new approach emerge in 2026 with tools like Scale and ZLUNA.
Okay, what do they do?
Instead of translating code, these compiler toolchains are attempting to take unmodified compiled CUDA binaries and run them directly on AMD hardware.
Oh, it's like building an emulator.
Exactly.
You just trick the software into thinking it's running on the original hardware so the developer doesn't have to change a single line of code.
Right. Now, it's still early and it's unproven at the massive scale of like a frontier model training run, but it completely shifts the battlefield. It acknowledges that the code itself is the moat, so you have to flow around it rather than trying to drain it.
So if lock-in is purely a function of software dependencies, that tells us exactly where we should look for cracks in the armor. I mean, there must be specific scenarios where the lock-in is weak enough that switching vendors actually makes sense.
Oh, for sure. The alternative market is very real, but it requires precise targeting.
Okay.
Take Intel's Gaudi line of accelerators. They are highly cost competitive for specific workloads, but they operate within a much smaller ecosystem. Typically, they make the most sense for enterprises that are already deeply entrenched in Intel server infrastructure and want a tightly integrated stack.
Right, keeping it all in the family.
Yeah.
And Huawei's Ascend chips are a major player globally too, right?
Yeah, they are, but they operate in an almost parallel universe. They run on an entirely separate software stack called Canon.
Right.
And that means an even smaller developer base outside of China, plus significant export control hurdles that Western buyers just don't have to navigate with AMD or Intel.
Which brings us to the most practical takeaway here. If you are listening to this and you're sitting in a board meeting tomorrow and your engineering lead insists you need a $10 million NVIDIA cluster, the first question you got to ask them is about the nature of the workload.
Yes.
Are we doing training or are we doing inference?
That is the ultimate dividing line.
Yeah, because training a massive new AI model from scratch requires the entire cluster to operate flawlessly for months.
Right, and that relies heavily on those deep NVIDIA-specific dependencies like NCCL.
Exactly. That is where the CD moat is a mile wide and a mile deep.
But inference, actually using the model to answer questions, sort data, or generate text is a completely different computational profile. Inference heavily utilizes highly portable frameworks like PyTorch, VLLM, or ONNX. And these frameworks act as an abstraction layer. They essentially hide the underlying hardware from the developer.
So for inference, you aren't directly relying on all those proprietary CUDA libraries. The framework translates it for you on the fly.
Exactly.
And that is exactly where a chip like AMD's MI300X becomes a massive, highly legitimate cost-saving option.
Yeah.
I mean, if software abstraction allows it, you can instantly realize that 40% cost reduction.
Yeah, which is huge.
And the briefing explicitly advises this. Never commit millions to a tender without running a cheap proof of concept benchmark. Just rent cloud GPUs from different vendors for a few $100s, run your specific inference workload, and measure the real-world throughput yourself.
Definitely. And to truly appreciate why those proprietary libraries like cuBLAS are so difficult to replace, we really have to look at what they're actually calculating.
The math.
The math.
Yeah.
The entire AI industry is built on a branch of mathematics called linear algebra.
Which sounds terrifying to a lot of people, but instead of getting bogged down in textbook definitions, let's treat these concepts as what they actually are, data structures for machines.
Right.
Because when AI looks at the world, it doesn't see concepts or words. It sees vectors.
Yeah, and a vector is simply an ordered list of numbers. But in artificial intelligence, that list of numbers represents a location in a massive conceptual space. This is called an embedding.
Okay, let's visualize that for a second. If you want an AI to understand the concept of a dog, it maps it across hundreds or thousands of different conceptual axes.
Right.
Maybe axis 1 is fluffiness, axis 2 is size, axis 3 is loyalty. And by the time it finishes evaluating the concept, the word dog is represented as a coordinate in a 4,096 dimensional space.
It's hard to wrap your head around.
It is. But it's basically just a vector of 4,096 numbers. And because it's a physical coordinate, the AI knows that the vector for dog is physically closer to the vector for wolf than it is to the vector for, say, toaster.
Yeah, and that is how a machine computes context. Now, if vectors are the inputs, the data flowing through the system, then matrices are the system itself.
Okay, what's a matrix?
A matrix is basically a two-dimensional grid of numbers. In a neural network, these grids represent the learned weights. They dictate how strongly one piece of data should influence the next.
Oh, so when OpenAI or Anthropic announces a new model with 70 billion parameters, those parameters aren't abstract concepts. They're literally 70 billion individual numbers organized into these massive spreadsheet grids.
Yes. And what's fascinating here is how the terminology scales up. The umbrella term for all of these data structures is a tensor.
Okay.
So a single isolated number is a zero-dimensional tensor. A vector is a one-dimensional tensor. A matrix is a two-dimensional tensor. And if you are processing video, you might have a four-dimensional tensor holding height, width, color channels, and time.
Which instantly explains why Google calls their custom AI chips TPUs, tensor processing units, and why the most famous machine learning framework in the world is called TensorFlow. Because the data literally flows as tensors through the network.
You got it. So the ultimate question is, how does the AI actually process these tensors to generate an answer?
How does it?
It uses an operation called matrix multiplication. You take your input vector, you multiply it element by element against the rows of the weight matrix, and you sum all those results together to create a brand new output vector.
Multiply and add. That's it.
That's it.
The entire magic of artificial intelligence boils down to multiplying two numbers and adding them to a running total, just done trillions of times a second.
Yeah.
And here's where it gets really interesting and why this connects fundamentally to the hardware. Think of a traditional CPU like a single master craftsman working at a weaving loom.
Okay, I like this analogy.
That one needle moves incredibly fast, darting all over the place, capable of weaving incredibly complex logic and conditional patterns. But it is still just one thread at a time.
Right, because a CPU processes sequentially. It's as brilliant at complex branching logic, but it's terrible at doing a million simple things at once.
Exactly.
Yeah.
But matrix multiplication doesn't require complex branching logic. It just requires doing the exact same simple math across a massive grid. So an AI GPU is like an industrial loom with 10,000 needles.
Yeah.
The needles aren't as smart or as fast individually as the master craftsman's needle, but they push through the fabric simultaneously. Because the matrix is a grid, every thread can be processed completely independently of the others.
And that is the essence of parallel computing. But the hardware designers went even further, right? Because that specific multiply and add pattern is the lifeblood of AI, NVIDIA built dedicated physical circuits onto their chips called tensor cores.
Right.
And AMD has an equivalent called matrix cores. These circuits do not handle general computing. Their physical wiring is designed to do nothing but ingest a grid of numbers, multiply them, and add them together in a single clock cycle.
And this is where the concept of mathematical precision comes into play, which dictates how fast those physical cores can actually run. We constantly see specs boasting about FP32, FP16, and FP8 precision.
Yeah, so FP stands for floating point. It dictates how many bits of memory you use to store a single number, which determines how exact that number is.
Okay.
FP32 is high precision. It is like calculating a trajectory down to the millimeter. FP8 is low precision. It is like rounding to the nearest foot.
But wait, if you round off the numbers, doesn't the AI get stupid? Like, doesn't the math fall apart?
Well, this is the brilliant resilience of neural networks. During inference, the network doesn't actually need microscopic precision to know that a dog is closer to a wolf than a toaster.
Right.
It just needs the general direction of the conceptual gradient. So by dropping from FP32 down to FP8, you shrink the physical size of the data.
Oh, I see.
That means you can shove twice as many numbers through the exact same physical wires on the chip in the same amount of time. You sacrifice a tiny bit of accuracy for a massive explosion in speed.
Which brings us to the ultimate bottleneck of modern AI hardware, memory bandwidth. Because we keep talking about these incredibly fast tensor cores doing the math. But those cores are utterly useless if they don't have numbers to multiply.
Exactly. If you have a model with 70 billion parameters sitting in memory, you have to physically transport those 70 billion numbers across the silicon die into the compute cores for every single word the AI generates.
It's a pipeline problem. You can build a factory that processes 10,000 gallons of water a second. But if the pipe feeding the factory is only an inch wide, the factory just sits there idling.
Yeah, just waiting.
That is why high bandwidth memory, or HBM, is so critical. The true speed limit of an AI chip isn't how fast it does math. It's how fast the memory bus can physically shove the matrix into the tensor cores.
And if we connect this to the bigger picture, understanding the physical reality of the math completely changes how you view the industry.
It really does.
An AI model is fundamentally a collection of massive number grids. GPUs exist purely because their parallel architecture is uniquely suited to multiplying those grids together.
Right.
And NVIDIA dominates the entire planet, not because their silicon is a generation ahead, but because they spent 20 years building CUDA to ensure that developers can route those number grids through the physical hardware with zero friction.
Zero friction.
Yeah.
The hardware gap is closed. The true currency of the AI boom is the switching cost of the software. But, that leaves me with one final thought, something for you to mull over that builds directly on the mechanical realities we've just unpacked today.
What's that?
Well, if NVIDIA's entire unassailable 20-year software mode is constructed around hyper-optimizing matrix multiplication,
Yeah.
what happens if the AI research community discovers a completely new mathematical architecture?
Oh, wow.
Like, what if tomorrow someone publishes a paper detailing a way to achieve machine intelligence that doesn't rely on grids of numbers at all, Does a 2-decade monopoly simply evaporate overnight because the math changed?
It really forces you to realize that no technological moat is permanent. I mean, if the underlying paradigm shifts, the deepest moat in the world suddenly just surrounds an empty castle.
It's definitely something to keep you up at night. Thank you for joining us for this deep dive. Keep questioning the consensus, always look past the spec sheets, and we'll catch you next time.